Hello students, good morning. So today we all are here to discuss our next topic, Hall's effect. We know fully well this is in your unit number 3. This effect was proposed by Edwin Hardwood Hall in 1879, basically used for semiconductors. So let us define this, what is the idea of Hall's effect. So when a metal or semiconductor carrying a current I is placed in a transverse magnetic field, capital B, then a potential will develop. This potential is perpendicular to the both current as well as the magnetic field. This phenomena is known as Hall's effect and was proposed by Edwin Hardwood Hall in 1879. So in short, we can write it as when a piece of conductor, metal or a semiconductor carrying a current is placed in transverse magnetic field, an electric field is produced inside the conductor or a semiconductor in a direction normal to the both the current and the magnetic field. This phenomena is known as Hall's effect and the generated voltage is known as Hall voltage. So many important properties we can find out by using this Hall's effect. We can easily find out the types of semiconductors, either we have p-type or n-type semiconductors. We can easily find out the mobility also as well as the carrier concentration. So these are basically the applications of Hall effect, either to identify the types of semiconductors, to calculate mobility or the carrier concentration of semiconductors. So this is simple arrangement proposed by Professor Hall, in which he has taken any type of material you can take, either p-type or n-type. Here we have taken n-type material. So along one direction we have taken current that is flowing along the x-axis. Along y-axis the potential is developed, and along z-axis the magnetic field is applied. So you can see the charge, this is only due to the Lorentz force, and along with the thumb rule, that is this charged particle which lie on the surface of this is moving from one surface to another, and they are all negatively charged electrons are shifted towards this side, and from the other side this is a negatively charged. So the this is positively charged and this one is negatively charged. So in between these two surfaces you can apply a voltmeter and we can easily measure the Hall voltage. So we have just applied electric field and magnetic field just by taking n-type semiconductor. This is the diagram. You can really you can exactly see this side. If we apply current along x-axis, magnetic field along y-axis, then automatically the polarization, the charges will shift along z-axis. So surface towards the U, that is A B E F, this surface become negatively charged and back side become positively charged. So by applying a voltage between these two, we can easily measure the Hall voltage. Similarly, we take the example of n-type p-type semiconductors. So this surface which is towards this upper surface, this become positively charged, back side become negatively charged. So this is only due to excess of holes. So p-type, as we know well, consists of excess in holes, and n-type consists mainly in electrons. So this is basically governed by the two fundamental laws. One is called a Lorentz force, second is called electrostatic force. So Lorentz force, we know well how to define Lorentz force. This is F is equal to QV into B. V is the velocity of the charged particle, capital V is the magnetic field intensity. So Lorentz force is given as QVB. This is a cross product basically, so we can say as QVB sin theta, but these they are mutually perpendicular to each other. So finally sin theta become 90 degree, so sin theta become 1. So finally it become only QVB. So here we have mu is the mobility, B is the magnetic field intensity, and this formula is given by QVB into B. So if we want to calculate Hall voltage and Hall coefficient, so these are two forces. One is known as electrostatic force. This is given by E into EH, This is QE simple, and second one is the we have just discussed electrostatic and electromagnetic. So magnetic is given by EVV because sin theta is equal to 1. So by balancing these two, we can find out EH is equal to V into B, because we can cancel the charge with charge. So second thing, we can also calculate the current density. So J is equal to NEV minus NEV. N is the concentration of current carriers. So maybe this is electron, this is holes. We want to calculate velocity. So velocity can be calculated from this formula. V is equal to J by NE. So this is a simple formula. V is equal to J divided by NE. So substituting the value of this V, we can substitute in this equation. So this EH becomes equal to VJ divided by minus NE. So Hall field is proportional to the current density as well as the magnetic field. So we can also write this as EH is equal to RH VJ and RH is equal to EH divided by VJ. So this simple formula, RH is equal to 1 upon NE. So this minus 1 upon NE for electrons, that means n-type semiconductors, and this become positive 1 upon NE, that is for, so either we have 1 upon NE or 1 upon PE. So P is for holes, N for electrons. So this is the way how to calculate Hall coefficient in your labs. So this is a simple diagram that we can use experimental setup, in which we have done one side we have applied electric field, current, and second side magnetic field, and the remaining side a potential will develop. So you can say here VH is the potential that we are going to measure it. So simple formula, this we have to find out the width of, if W is the width of a specimen across the sample, how width is done there. So EH is equal to VH divided by W. W is the width of the specimen. So as we have already calculated, so RH is equal to EH divided by VJ. So just by substituting the value of this EH, VH by W, so finally we have the formula RH is equal to VH upon W VJ. So this formula we normally use for experimental calculation for Hall's coefficient. As well as we want to calculate carrier concentration, we can use some formula 1 upon NE, RH is equal to 1 upon NE. So we can also calculate current density also. So J is equal to I by A. A is the area of cross section. So area of W is the width, T is the thickness. So multiply these two gives the area. So by substituting this value, we can finally calculate VH in terms of W and T also. So VH is equal to RH W VI divided by, so this we have already calculated earlier. So this just we replace this area by WT. So finally WW cancels. So this is RH IB divided by T. So this is a simple formula used in labs for calculating the Hall voltage, as well as, or we can calculate Hall coefficient also.